Hello, everybody. Welcome to today's seminar. Please place yourselves on mute, and also please note that this seminar is being recorded and will be placed online. If you have a question, you can use the chat box or the email address that you can find on our seminar series website to address questions to the speaker, which we will read out at the end of his presentation. Today's speaker is Dr. Elsayed Talaat. He works for NOAA, where he is the director of the Office of Projects, Planning, and Analysis for Satellite and Information Service. Leads in the development, integration, installation, and acceptance of major system elements such as spacecraft, instruments, launch services, and ground systems for NOAA's operational environmental satellite systems, and in particular for the Space Weather Follow-On mission, which he will be talking about today. Please go ahead, Dr. Talaat.
All right. So let's try this. Oh no. Oh no. Zoom is, sorry, allows, okay. Will not be recorded contents until it is quit. Quit now. All right, can you see my screen?
No, not yet.
All right.
Okay, don't worry too much. Try a little more, and if you can't, maybe you can.
There we go.
Can, yes.
There we go. All right. Hello, everybody. Thank you, Dave, for the introduction. So today I'll be talking about the Space Weather Follow-On mission, but since I was given a little more time than originally planned, I figured I'd talk step back a bit and talk about NOAA's current and future space weather architecture around the Space Weather Follow-On program. And so let's see if this. So what do you see? Do you see the full screen?
You see the clips off to the left too.
Okay, let's try playing. How about that?
Perfect.
All right. So NOAA is an operational agency, so we are driven by our operational needs and our requirements, and that means for space weather, we're driven by the needs of the Space Weather Prediction Center within the National Weather Service. So this is the official source of space weather alerts, watches, and warnings, provides 24/7 analysis and forecasting of space weather storms, and particularly looking at warnings on geomagnetic storms, solar radiation storms, and radio blackouts. And then this service also feeds into or coordinates with the Department of Defense services provided by the 557 Weather Wing in the Air Force. So what NOAA has the way that the SWFO makes its predictions and nowcasting and forecasting is through a suite of sun to earth modeling capability. Some are empirical and some are first principles, and hopefully some in the near future will be assimilative. But from the sun, we have the WSA model that's been operational since 2011, and out into the solar wind and the heliosphere, we use NLIL to propagate the solar wind forward. At the magnetosphere in 2016, we adopted the SWMF model from University of Michigan to drive the magnetospheric currents and then down into the ionosphere and the ground. Magnetic perturbations down there, and that's driven by upstream measurements of the solar wind. And in the ionosphere, we have operational this year the ionospheric model from built in the University of Colorado. And in the thermosphere, we have the whole atmosphere model that's coupled to the numerical weather prediction model that's used by the Numerical Weather Service, the National Weather Service, that's also operational this year. And the groundy field, which is critical to one of our major stakeholders, the power industry model, has been operational since 2019, and that's driven by the theoretical models that are running there. Oops. And so all of these models are driven by observational data. For the surface of the sun is primarily viewed from the ground currently, but the solar wind and is measured in situ at L1, and of course coronal mass ejections are viewed remotely off the sun. So we provide the spaceborne measurements for the National Weather Service, and this year represents a kind of a major shift in how we do that. Now that we have established a space weather follow-on program, we're going to build a space weather program around that. So to reliably monitor space weather from L1, GEO, other orbits, etc., and LEO as well, and look at capabilities from L5. So this represents a shift and evolution of how NESDIS is prioritizing, NESDIS, which is the satellite arm of NOAA, is prioritizing space, oops, keep doing that, sorry, go back. Space weather is now part of a three-legged structure, along with the geostationary and low Earth orbit spaceborne platforms for terrestrial weather. So the space weather program was developed specifically to address very high priority measurements, continuity of measurements that are needed. The coronal mass ejection imagery, and the primary source is the ESA NASA SWFO spacecraft, which is solar power limited to 2025. And Discover and ACE, which provide the in situ upstream magnetic field and plasma measurements of the solar wind that give us advance warning. And these are not likely to last by the mid-20s. So we had a very strong imperative need to set up a program to refresh those capabilities and maintain continuity. So we're implementing this by flying a 3-axis stabilized ESPA-class spacecraft out to L1 that's going to host a suite of in situ measurements as well as a coronagraph to make CME imagery. And also a ESA contributed instrument, an X-ray flux monitor, is going to fly on board as well. It is going to be ride shared with the NASA IMAP mission, so we have a very tight schedule to implement this, but also a schedule that will allow us to get up there before the anticipated failure of the assets that we rely on now. And so this has been enabled by the coronagraph development that we have been funding at the Naval Research Laboratory for several years now, at varying levels of effort, and that has come to fruition, and where we expect the first compact coronagraph to fly on the GOES-U spacecraft, and then the second compact coronagraph to fly on this SWFO L1 mission. So the other part, as I alluded to, is flying a coronagraph on the GOES-U platform. GOES-U, which is its mission is to observe terrestrial weather as well as in situ space weather and solar observations as well. Manifests a suite of solar instrumentation on its solar panel arm, and this solar pointing platform is has the SUVI instrument, the EXIS instrument, and we've been able to make room for the C-Core, the compact coronagraph, on there as well. And so this nominal launch for that spacecraft is also 2024, and this will provide resiliency to the very critical upstream, or I mean, the forecast capability that we need with coronagraph imagery. And I should say that if there's questions, please speak up. I don't know the format of these talks, but I welcome questions as we go along. So as I mentioned, we have a very tight schedule in terms of development and procurement. And so the chronograph is being built at NRL, but the other instruments are being procured. We've made selections for the solar wind plasma sensor, which is going to be built by UC Berkeley, and the magnetometer, which is going to be built by SWFO and University of New Hampshire. And we're still in blackout phase for the selections for the suprathermal ion sensor. These are instruments that are going to fly on the SWFO L1 mission, and the spacecraft as well. So we hope to have all selections made for the instruments and spacecraft by this summer. The SWFO antenna network, we also have a ground system that's being developed to receive the data from space weather follow-on mission, the L1 mission. And that because the sun stays in the same place and the Earth rotates, we need to have a distributed set of satellite antennas around the globe, and that's the space weather, SWFO antenna networks. We're going to leverage as much as possible partner ground networks and the current real-time solar wind network as appropriate, but we do need to have at least 3 or 4 sites around the Earth that are capable of receiving data in X-band for the science data and S-band for commanding. And then this data is going to flow into the National Satellite Operating Facility, or NOAA Satellite Operating Facility in Sweetland, Maryland, where it's going to be distributed both to SWFC, the Space Weather Prediction Center, and the National Center for Environmental Information, which is part of the satellite division at NOAA. And the SWFC will provide the real-time products to its partner space weather organizations and other users. And NCI will provide the retrospective products to the user community as well. So in the last 2 years have been a very dynamic time for NOAA and NESDIS. We were able to secure funding in the NOAA budget for L1 coverage. We have begun flight fabrication of the compact chronograph and secured funding for the compact chronograph on GOES-U. We established a joint project office with NASA to implement this the space weather follow-on program, both that goes in GOES-U and for the L1 mission. We have an agreement with NASA IMAP mission for a ride share for SWFO L1, and let out procurements for the instruments. And then, as I also mentioned, from a space weather standpoint, we have a couple of other new developments, which is launching the Cosmic 2 mission with Taiwan, and formulating arrangements with ESA for data sharing with their planned L5 mission, and negotiating with ESA for possible instrument exchange in the future. So as I mentioned, this year we were able to, along with Taiwan, oh, that's interesting. This is a interesting squiggles happening there. We were able to with Taiwan and the Air Force, launch a 6-satellite constellation about the equator at 24-degree inclination. That in each satellite has 3 instruments. The main one is a radio occultation sensor, that a receiver that both makes neutral atmosphere soundings as well as ionospheric soundings. And with these 6 satellites, sounding both off of GPS and GLONASS, we have very dense coverage, about 4,000 occultations per day, at least 4,000 occultations a day, with 30-minute average data latency of the ionosphere. Actually, we're approaching 30 minutes average data latency. We're still a little high on that. It should be medium latency as well. So the design lifetime is 5 years. This was launched last year in June 25th. And here, the other image you can see here is the deployment of the last Cosmic 2 spacecraft off the STP stack. STP-2 launch had 20-some odd payloads on it as well. We were one of 2 primary payloads, and it was a highly successful launch for the Air Force and SpaceX. So this is the type of coverage we're getting in the ionosphere. The orange dots are what we're getting in the ionosphere from Cosmic 2, and the blue and green dots are our partner data, which unfortunately do not include ionospheric measurements at this time. The METOP series at EUMETSAT is looking to see if they can add ionospheric occultations to their measurement scheme, but currently right now it's only Cosmic 2. So this slide here just gives us an idea of, in the near term, where we think we're going in terms of observational capability, where we have SWFO L1, we have the geostationary ring about the Earth, where many of these geostationary satellites have in situ particle measurements. The ones that NOAA builds have also magnetometer measurements, and we also have partnerships to get occultations and in situ measurements in low Earth orbit as well. But we really want to look towards the future, and so we are sponsoring, along with NASA and NSF, a space weather operations research infrastructure workshop. It's going to start tomorrow, and I'm not ashamed to say that I'm using most of the slides I'm presenting there, test run here. Thank you for giving me the opportunity. But this workshop is going to consider options for technology, instrument, and mission development to support in situ and remote sensing space weather observations from ground or space-based vantage points, including all sorts of orbits that the community may think is beneficial to our operations going forward, as well as research infrastructure going forward. And so this has been enabled by an ad hoc organizing committee. We have a virtual workshop Tuesday and Wednesday of this week, and then we have a second follow-on in-person, hopefully, workshop in September. But of course, we'll plan for contingencies to have it virtually as well. And then a follow-on workshop that's primarily supported by NASA and NSF to address out-of-scope issues encountered in the first workshop here. So the main thing about this program is that the starting point is the 2025 program of record, where we start from the observations. Excuse me.
Daddy, did you respond?
No, not yet. Okay, where we start from the observations we have. We plan to have in space and be utilized by our space weather prediction center that includes the SWFO L1, GOES-U, Cosmic 2. We're looking at how we can use NASA Gold imaging of the thermosphere ionosphere, the METOP-C, hopefully ionospheric data is going to be available from there, and ESA L5, which is actually slated for 2027, but in the scope of our planning here, we consider it part of the program of record and development. And so kind of the evolution of this is that we see L1, L5, we see more opportunities for sounder sats in low Earth orbit, and hopefully growing opportunities for additional measurements at in tundra, in the tundra orbit that can provide some of the space weather measurements that we don't currently have at high latitudes, as well as additional solar imagery. And I'll just one slide that I like to have. It's kind of a open canvas right now about what we need for an infrastructure. If we pull out a little bit from Earth, and of course this is not the scale, but in terms of the coverage we have, obviously we might want to think of as we further explore out further into space with human exploration and space commerce. Well, we may need a space weather architecture beyond just protecting the Sun-Earth line. So, and this is my last slide here. Just again, a plug for the National Academies workshop that is going to happen tomorrow. This is going to start tomorrow.
Great. Thank you, Elsayed. We have a few comments and questions for you. The first one is several people marked down that they think there's a typo on one of your early slides. And since you're going to show them tomorrow, let's fix that.
Excellent.
They believe that STIS is by UC Berkeley and that SWIPS is the instrument not yet selected.
Oops. You are absolutely right. That is absolutely true. Thank you.
Okay, good. The next comment or question is from Pat Rife, and she notes that many people use real-time data streams from NOAA sources for their own space weather forecasts. And she would like to hope that that will continue to be true in the future as this architecture goes forward, that they'll be available. Is that likely?
Absolutely. Yeah. I mean, we plan to have open open data in real time as well. It's the same sort of data provision that we have now.
Okay, super. And the last question is from Jason Durr, and it's on the topic you concluded with. He'd like to know exactly how can outside people participate in these discussions, or at least listen to these discussions tomorrow and the next day. Is there a website he should go to?
It's www.nationalacademies.org/events.
Okay.
And you'll see it listed there. And I believe there is no registration, no limit, as far as I know, to participation.
And I see that Kyle has just posted that website in the chat box. Anyone wishing to see that can see it in the chat box. This is recorded, so Kyle is going to be posting this presentation. And so if you can't quite catch it now, just look on our YouTube channel later this evening or early tomorrow, and you'll find that website listed that Elsa had pointed to. Okay, that looks like it's it. If there are no further comments or questions, I'd like to thank Dr. Talaat for joining us today and look forward to a successful meeting the next couple of days. I hope many people here can join you. Thanks, everybody, and thank you especially to Dr. Talaat.
Thank you very much.
Bye.
Bye.